Hello again and welcome to another video lesson with A.K.A. Lawson. In this lesson we're going to start looking at free fall, or essentially a special circumstance of one-dimensional motion. When an object's in free fall, it just means that it's only under the influence of gravity. There's no other forces acting on it. Essentially, if you're something flying through the air, you can't have wings or a propeller or something that would create a significant lift while you're in motion. That means something like a rocket being launched during the initial part where the fuel is being burned and it has thrust going upward, it is not in free fall. However, as soon as it stops using its fuel, it then enters a free fall situation. We'll also look at instances where there is a significant drag, where you have something like a parachute or some other feature, either due to the shape or the viscosity of the fluid that you're flying through, and that can have an influence on how you behave, although again, the only force acting on you will be the force of gravity, other than air resistance or drag. As was mentioned, free fall really is just a special circumstance of one-dimensional motion. And what's convenient about free fall problems is that the acceleration is generally known, either because we're in an instance where air resistance is negligible and the acceleration is acceleration due to gravity based on the gravitational field that you're located inside of. On Earth, that acceleration is 9.8 meters per second towards Earth. We're just going to use the general term lowercase g, which could be the acceleration due to gravity on the Moon or Mars or someplace other than Earth, although many problems will be on Earth where g is a known constant. You can choose whether or not to continue to use the acceleration in the y direction as a sub y, and just know that a sub y represents the acceleration due to gravity for these types of problems. Or, as in most cases in many references, you'll see that we use lowercase g to specify that the acceleration experienced is acceleration due to gravity. Gravity can only attract objects towards each other, so that acceleration is always towards the surface of the object that you're experiencing the gravitational field from. Thinking about being near the surface of Earth, it pulls us towards Earth. It's also interesting and a little bit counterintuitive that these are mass-independent descriptions. Without any air resistance, or when we have negligible air resistance, if we had two different masses, perhaps one we could call mass A and one we could call mass B, both would experience the same acceleration due to gravity, both would experience the same change in velocity over the same displacement and the same amount of time. We'll get a more thorough explanation about why these are mass-independent situations when we're looking at forces later on in the curriculum. When you have significant air resistance, or when air resistance is not negligible or ignored, we end up having a little bit of a special circumstance. What happens is, as the velocity increases, that air resistance increases. It's not a constant value, it's actually velocity dependent, which means the acceleration of an object when air resistance is not negligible is also velocity dependent. That's shown down here, where we see that the acceleration in the y direction is actually equal to g, that constant of acceleration, minus kv, where k is some constant. That constant depends on the viscosity or the properties of the fluid that you're moving through and the shape of the object as it moves. As you can imagine, something that's aerodynamic would have a smaller k, while something that lacks the features of an aerodynamic structure or shape would have a larger k value. And then, of course, moving through air is much different than moving through water or some other type of fluid. Given that the acceleration in the y direction, when we have air resistance that's not negligible, is velocity dependent, something interesting happens when we start thinking about how that acceleration decreases as the velocity increases. What we're really saying is there's some point at which the velocity gets large enough that the acceleration goes to zero. We refer to that as the terminal velocity. An object reaches terminal velocity when its acceleration is zero during that free fall. Note, it does not stop falling. It continues falling towards Earth. It just stops accelerating. It stops speeding up. Looking at this statement, the acceleration, which is the derivative of velocity in terms of time, is equal to that acceleration of gravity minus that constant times the velocity at that time. While we notice this is a differential equation, at the moment it might be not be obvious how we can deal with this. Just a little bit of algebra, and we notice that differentiating 1 over g minus kv would be equal of time. Now we can integrate both sides of this, going from time 0 to t, and for this example, we're going to imagine starting from rest, or an object being dropped. We're going to go from an initial velocity of 0, or being at rest, to some final velocity. You'll notice that's not necessarily the terminal velocity. If enough time goes by, that would be the terminal velocity, but this equation will actually work for any time between the initial velocity and reaching that terminal velocity. The integral of 1 over g minus kv, that ends up being a little bit of an annoying integral. But by doing the substitution, that's really the integral of 1 over u in terms of u being equal to the integral from 0 to t, or in terms of t. Notice I'm not worrying about figuring out what these bounds are of u, because it's just to be able to do the substitution integral here. That's going to be the natural log of u, which is g minus kv, over the integral of g minus kv, or negative k. And we're going to subtract from that the natural log of g minus k times 0, which ends up being 0, over negative k, and that'll equal t minus 0. Notice we can multiply both sides by negative k, and when you're subtracting one natural log from another, that's equal to the natural log of the ratio or quotient of those two functions. So what we get from that is that the natural log of g minus kv divided by g is equal to negative kt. Take the exponent of both sides, we do the e to the negative kt will end up equaling g minus kvg, and let's give ourselves some room. That means g minus kv divided by g is equal to e to the negative kt. Again, I'm trying to get this as a velocity function. Get the velocity in terms of time. It's not too bad. If I multiply both sides by g, then add kv to both sides, and then subtract e to the kt, what we really see is that the velocity as a function of time is going to end up equaling g over k times 1 minus e to the negative kt. Mathematically, this actually makes a lot of sense for several reasons. One is we notice the terminal velocity is when the acceleration is 0. If we look back at our acceleration function, what we're saying is when will 0 equal g minus kv? That's going to happen, or v terminal in this case, that means v terminal is going to end up equaling g divided by k, which matches our function. When t gets very large, e to the very big number gets closer or approaches 0. And so what we essentially have is 1 minus 0, or 1, or when t is large enough, the velocity at that time is g over k, or our terminal velocity. However, when we have not reached that terminal velocity, when t is not a large enough value based on that k constant, then we're at some velocity before we reach our terminal velocity, and we're still experiencing some acceleration, although the acceleration decreases over time. It's good to think about or imagine what would the acceleration as a function of time and what would the velocity as a function of time look like. As our velocity increases, our acceleration is going to approach 0. But our velocity is not increasing at a constant rate. The faster it goes, the slower it increases. With air resistance or drag, that acceleration is going to decrease and approach 0. At that time when it essentially goes to 0, is when our acceleration, or when we've reached terminal velocity. And if we're looking at our velocity as a function of time with drag, the velocity will start at 0 and reach some point where it remains constant. Without drag, the acceleration would be a constant horizontal line, and the velocity would be a constant positive increase. When we have an object released from rest, again going back to the instance where we consider negligible air resistance, or when we're undergoing a constant acceleration due to gravity, our UAM equations become very handy and allow us to simplify several problems. When you start from rest, or when you drop an object, they naturally simplify themselves. One of the functions we're used to, which is v final equals v initial plus acceleration times time, but since initial is 0, what we're really saying is that the velocity in the y direction equals the product of acceleration in the y direction times time. V as a function of t is going to equal gt, where again we have to be a little bit careful. Down being positive, we would have a positive g and a positive velocity at any instant in time. If we make down negative, then we'd put in negative for a g, and we'd have a negative velocity at every instant in time. Final position equals initial position plus v initial times time plus 1/2 of the acceleration times time squared. But if the initial velocity is 0, what we're really saying is that y at some point after is equal to our initial position. Sometimes we would refer to that as an initial height or altitude, plus 1/2 of that acceleration due to gravity times time squared. Again, being a little bit careful about whether or not we're assigning an up or down as a positive direction. We get a negative g, we get a negative change in position, although the position might not be negative depending on where we started. If we start at the origin, and we're moving down, and down is the negative direction. But if we start at some height above the origin, where we assign the initial position a positive value, then as it falls, that's just going to approach 0, especially if we make the origin the ground, then it will never actually reach a 0 position. V final squared equals v initial squared plus 2 times acceleration times change in position. However, since our initial velocity is 0, our velocity as a function of time squared is going to equal 2 times the acceleration due to gravity times our change in position, or our vertical displacement. Again, being careful about assigning down as a positive or negative direction. If we assign down as a negative direction, our displacement will be negative and our acceleration due to gravity will be negative. If we assign down as a positive, then they'll both be positive. Also be cautious. This is a square that we're going to be solving for. If we're solving for the actual velocity, the velocity as a function of time is going to equal the square root of 2g delta y. And you have to remember, the square root of a value like 100, the square root of 100 is not 10. Everybody assumes, because when they put in their calculator, they get 10. But indeed, it is plus or minus 10. This function doesn't tell you whether or not the velocity is positive or negative, because either of those is an acceptable solution. So you have to think about what you're doing. If you're assigning down as a negative direction, then the negative solution is the correct answer. While if you assign down as the positive direction and it's moving down, then the positive is the correct sign to be on your velocity. There's a couple of instances that create a little bit of difficulty when we talk about an object undergoing free fall, whether it's thrown upwards or thrown downwards versus something that's been dropped. When something is initially launched or thrown upwards, it has to spend some time moving in that direction while it accelerates in the opposite direction until it reaches a point where it's 0 and then starts returning or falling back down. Knowing that at the top of its trajectory, at that maximum altitude or the maximum height, the velocity is instantaneously 0, allows us to answer questions about on the way up versus on the way down relatively easily. It's also symmetrical as long as you land at the same height you were launched from. If I throw a ball up and catch it at the same height I launch it from, it'll spend half the time going up and half the time coming down as it goes up to that 0 velocity and then returns back to the hand. If air resistance is negligible, it'll also land in my hand at the same speed that I launched it upward. So the velocity is symmetrical in terms of it having a negative sign or opposite direction but equal magnitude velocity at the same altitude. Because it has a constant acceleration but a changing velocity, it will be half the velocity when going halfway up the trajectory. However, it will get up in less than half the time, because as it increases its altitude, as it gets closer to that apex where it stops, its velocity decreases. So the amount of time it spends or takes to cover the final little bit of height is actually greater than the amount of time it takes to cover the initial little bit of height, just because it's traveling at a smaller velocity. One of the things that's interesting to think about is throwing a ball upward and dropping another ball from the same cliff. When you drop the ball, it'll have an initial velocity of 0, so it will accelerate due to gravity along that entire height. The ball that was launched upward, it'll actually spend more time in the air because it has to reach its apex before it falls. But that's essentially the same as dropping a ball from a higher cliff. It's going to hit the ground with a greater speed, because when it passes back by that initial launch position, it's going to have an initial velocity going downward. If we drop a ball and throw a ball downward from the same location, they have different initial velocities. And because the ball was thrown has an initial velocity, even though they experience the same acceleration, that initial velocity with the same acceleration means that it will constantly be going faster than the ball that was dropped. And in fact, over time, it will be increasing its velocity at the same amount, but because it was already going faster, it's going to continue to go faster and faster, or increase the distance between the two objects. While if there was an object dropped from a lower altitude, so it started at rest, and we threw an object from a higher altitude downwards towards it, since it has a larger initial velocity, even though it's at a higher altitude, it will close that gap between them. And if enough time of free fall is available, it will actually catch up and pass the object that was dropped.